Welcome to all of this session. Now we'll see the problems regarding the kinematics of fluid. Whatever the question came in the GATE examination or any competitive type examination, and types of the problem we'll segregate and we'll try to do this kind of the problems. Overall concept. And I will recap our concept in the theoretical concept, whatever we have learned in the previous lectures regarding the kinematic topics. Okay. So I am directly coming to the slide. So here. So first question, we have already completed the theoretical portion last day. So first question is coming that is a GATE 2021 mechanical question 1. So for a two-dimensional incompressible flow having a velocity component u and v in the xy direction, it is a Cartesian coordinate given. One expression has been given here. The expression is given here, del u square del x plus del uv del y. That can be simplified to the followings. So first thing here that had been mentioned here, so incompressible flow. So incompressible flow, as it is the incompressible flow, we know that for as it is the incompressible. As this is a incompressible flow. Incompressible. So only it is a two-dimensional case because only x-axis and y-axis has been given to you, 2 dimensions. So divergent of velocity vector is equal to 0. So only first component du dx plus del u del x plus del v del y is equal to 0. We are getting from this incompressible flow concept. Now one certain expression is given to you. This expression you will come to know that this one, del u square by del x and del uv by del y. This expression is given to you. If you extend this expression, it will comes in this way, 2 del u del x. 2 del u del x plus, in this part, first u take common, u del v del y plus v del u del. From this part, so there are 2 del u del x. So from here you take 1 del u del x. Sorry, 2u, sorry. Here it will be 2u del u del x. So 1 u del u del x plus another u del u del x. The 2 part. Same. 2u del u del x is a 2 part. And here you take u del v del y plus v del u del y. Now this term u du dx1 and u dv dy, if you take this to single side, so u into del u del x plus del v del y plus the remaining part. Remaining part is this one and this one. U del u del x plus v del u del y. So as it is an incompressible flow, this part is 0. As it is an incompressible flow, this part is 0. So this expression has been reduced to U del U del X plus V del U del U. What does it mean? The advective X component of acceleration. This is nothing but the advective. The expression which has been given is the advective component of X acceleration along X-axis. This expression you can know advective or it is special code components, advective components of X. Acceleration along X-axis. So your answer will come is the U del U del X plus V del U del Y. This is your answer for this question. That is the type of the question. It's simply you use here the incompressible flow equation. That is the concept here. Next, another type of the problem is given in the same GATE 2021 mechanical set 2. A two-dimensional flow having a velocity is given, U and V is given, two-dimensional flow. So two-dimensional flow, U is given as a 2xyt and V velocity along y-axis minus y squared t, where the t is the time, the total. Now the equation of the streamline passing through x is equal to 1 and y is equal to 1. So streamline equation. So streamline equation, if you recap the streamline equation, it was like that dxu dy. As it is two-dimensional, only two components yet. That is the streamline equation. Dx by u is equal to dy by v. Just simply put here this u and v. Dx by 2xyt and dy by minus y squared. So t will be cancelled out from the both sides. And one y will be also cancelled out. So the finally dx by x is equal to 2 dy by minus. Now if you do the integration on the both sides, so it will comes ln x will come minus 2 ln y plus ln c, some constant. So if we take this part, it can be written as the ln y square plus ln c. You take this ln y square on this side, so you can write it down ln x plus ln y square is equal to ln x. Hence, xy square ln c. So xy square is equal to c, constant. So they're asking for at x is equal to 1 and y is equal to 1. So in such a cases, c is equal to also 1. If you put here value x and y, so your streamlined expression will be xy square is equal to 1. That's your answer. So this way you have to solve this problem. So here you have to simply directly put the streamline equation. They're telling you streamline equation about it. Directly you know the streamline equation. Directly put u and v is given. From there, after doing integration, you are getting this. That is the straightforward method to get such kind of a problem. That is another question is coming, the GATE 2019. So GATE 2019, the question is given, water flows through a pipe. A velocity is given. What is the velocity? Velocity is given to you, V 4 by T plus X plus Y. So velocity is only along y-axis. So only small v exists. U is equal to 0, W is equal to 0. Because only J component is here. In such a cases, you are asked to find out the total acceleration at a point. You are asked to find out the total acceleration at a point. So as U0, W0, so AX component will be also become 0 and AY component will also become 0. Because as U0, W0, sorry, AZ. So only remaining component will be the AY. And what is AY? If you extend the AY, it will be like this way, del V, del T plus U, del V del X plus V, del V del Y plus W, del V del Z. That is the equation. So U is 0 here. You have seen there is no U component for the velocity. So U is 0, W is 0. So the acceleration dVt by v dv. That's all. So if you directly, your value is given to you, v is given to you. So small v is equal to 4 by t plus x plus y. So if you do del v del t, it will comes minus 4 by t square. So you can put here minus 4 by t square. And the v value is already given to you, 4 by t plus x plus y. And here in this expression, dv dy, if you do this operation, it is simply 1 into 1. So that is your acceleration value. So t is equal to, given as a t is equal to 2. At t is equal to 2, xy is equal to 1 and 1. So we put it here. So t is equal to 2 means 4 by 4 plus 4 by 2 plus 1 plus 1. So it is minus 1 plus 4. So 3 meter per second. This way we have to do the problems. That is the simple logic we are taking in this one. So if they are asking about the acceleration vector is only because AX is 0, AY only exists, and AZ is also 0. So this is 0, this is 0, so 3J. At this point, the acceleration would be 3J. So that's why we can solve this kind of a problem. You can verify the calculation. If there is any mistake, you can tell me. You can write it down. But the process is like this. It should not deviate from your own equations. Simple way. That is the type of the problem. Acceleration, we just recap the formula of the acceleration and we do this. If it is a u is equal to, if u w is persisting, so there may be ax will be persist or az may be persist. So then problem will be more complicated in that sense. This one kind of the problem is given to you. Here simply you see that one flat plate is there. One flat plate here. This is the plate which is falling down with the velocity which is falling down, or it is the flat place is pushed over the liquid. In that place there is a liquid. In this place there is all liquid. This liquid is there. Now the plate is moving downwards. The plate is moving downwards with the velocity u is equal to 0.01 meter per second. So the plate is downwards. So where the fluid will escape? The fluid is escaping from the open side. This one side is the open side. Another here that there is another open side. So whenever the plate is coming down, the fluid is escaping from in this path. The u average, then they're asking what is the escaping velocity, average velocity of the fluid. The average velocity, u average, you have to find out. You have to find out of the fluid, which is draining out at the instant. The average they're asking. In that case, you have to take the integral method of mass flow rate. What is the integral method of mass flow rate? If you remember, we have done it in the, so at here rho you can take it constant. There is no change of the rho. We can consider there is no change of it. It's a constant density. Already written as the incompressible flow, but further we can tell it's a constant density flow. There is no change of the rho. So the u into the area of the plate, that is the volumetric flow, because it is coming down. So same amount of the liquid is going out from here. The same amount of the liquid is going out. That is the u average into this area plus this area. This area plus this area. What is that area? This area is exit area. Area of exit. U is given as a 0.01 into the area of the plate. The area of the length of the plate is given L, and the perpendicular to the length, you can take it any width. If there is a width of the plate W, perpendicular to the plate, that should be is equal to U average into exit plane. Exit plane is the D. So two, both sides. Here D into W here. Here also D into W. It's like this one. It's a D. This side is perpendicular to the plane is the W. As the exit plane. Similarly in this side also. So 2D into W. 2D into W. L is given here, probably. Length is given. So 0.01 into the length. Length is given 1. W will be cancelled out from the both sides. 2 U average into 0.0. This is 0.1. D is equal to 0.1 meter. So hence nothing, that is the remaining part is the simple U average is equal to 0.01 by 0.2. So it is coming nearly 0.05. It will come nearly 0.05. 1 by 20. So 0.05 meter per second. So the fluid velocity, average velocity, we are talking about that is the average. So if the velocity diagram, if you're taking, it's the average. Uniformly, it is going out. There is no slip condition. It's not satisfying here. Uniformly, it is going in this direction. Similarly, on the opposite direction, also it is going uniform. Or average part we are taking into consideration. U average. In that side also, U average. Over the area. Area is 2D. That is this way we have to solve this problem. Mass balance or continuity equation, the basic sense we are applying here. As the plate is coming down, it pushes the liquid. So liquid is trying to escape the escaping route. The escaping route is the side. So from the side, the liquid is going out. This is the way to solve this problem. Another problem is given here. One two-dimensional incompressible flow field is given. The two-dimensional incompressible flow field, where the velocity is given here, velocity vector AXI minus AYJ. As the velocity vector is given. So that is an incompressible. Already told it is incompressible. So incompressible flow continuity equation is, we know, du dx plus dv dy. What is that? So this is the u part, small u. This is the v part. So if you do this operation, du dx, it will come as a a. If you do the dv dx, it will come minus. So this is part. So a minus a will come 0. So it is satisfying the continuity equation also. It is satisfying continuity equation. So it is true. First statement is true. Second statement purpose, the streamline. Second statement and third statement purpose, we have to go for streamline equation. Because streamline equation, if you are going to get it, so dx by u, dy by v. U is given as a dx by ax equal to dy by minus ay. A will be cancelled out. So dx by x minus dy by y. If you do the integration in here, so ln x minus ln y plus ln c. So hence ln xy is equal to ln c. So xy would be equal to the c. That is the streamline equation. So streamline equation is xy into constant. Xy is a constant. What does it mean? It means if x tends to 0, y should be infinite. So second statement also true. Because in that case, if x tends to 0, y should be infinite. In that case. Next thing is so first statement is true, second is true, third one is not matched. x is equal to, because it is rather than the xy is equal to constant. So this equation. So this is the answer, is the false statement. This statement is the false statement. But what about the fourth one? We can verify the fourth one also, whether it is correct or not. So if we want to verify the fourth one, just for, so you along x-axis velocity ay, along y-axis velocity minus ay. So E rotational means the curl of velocity vector is equal to 0. So you can go for the curl operation. So curl operation, if you go, is the basic procedure. That's why I'm going it for it. Ijk del x del y, no z term. Here ax minus ay. So only k term is existing. So k of d dy of ax. So d dy of ax minus d dx of minus ay. So as here no y and here no x, so it will be automatically a null vector. So it's a null vector. That's why you can say it is a irrotational flow. At the curl of the velocity is a null vector, so it's a irrotational flow. So this is correct. This is also correct. This is also correct. So only false term is this one. So this is the answer. You're asked which statement is the false in here. So that's the way we have to solve. Another cases is given in GATE 2017. Regarding the velocity vector, two-dimensional velocity vector is given, which satisfy the incompressible equation. So incompressible flow equation which satisfy. U and V is given. Very simple question here. Just we'll see. U is given here 5 plus A1x plus B1y. And V is given here 4 plus A2x plus. So incompressible flow equation, it is satisfying. So incompressible flow equation, divergence of velocity vector is equal to 0. What means that du dx plus dv dy is equal to 0. It is satisfying this equation. If you put here, so if you go for the du dx operation, it will come A1. If you go for dv dy operation, it will come B2. So A1 plus B2 is equal to 0. This equation will be satisfied. A1 plus B2 is equal to 0, so answer is B for this question. This is simple, just we are putting the logic in here one by one from our previous concept. Any kind of question, if they are asking in a GATE, you have seen so many questions they are asking, but typically they are using the same concept more and more time. Next thing is the volumetric flow rate per unit depth between two streamline having a function. Last day we have done it, this part, but again I am interested to show you another method to do it. The first question I am considering, I am taking the first question. Second question is the repeating question. So first question, the volumetric flow rate per unit width. So first, yesterday, if you remember, I will take one small elemental length dl, and from that side we are taking it, which is a part of the dx and dx. This is the dx and dy. Yesterday we have taken this thing. So there is a u velocity is in this side, u into minus I. And yesterday we are doing this in this way. And V into That is the velocity vector. So whatever the flow is coming from this path, vertical path, whatever the flow is coming across the vertical, whatever the flow is coming across the horizontal, that will mix up. And the total flow will go out through the element. This concept we have taken yesterday. So flow through dy plus flow through dx will be the flow through dl. This concept yesterday we have taken. Without taking this concept directly, we can also do this kind of the things. So yesterday we are taking in this way. So what are the, so we know V dot dA is the flow rate. V dot dA is the flow rate across the section. So flow rate across dy plus flow rate across dx is equal to flow rate across. Yesterday concept was like this. One control volume, you choose it, and through the control volume, the entry is a steady condition. So entry is equal to the exit is the same. This way we have solved this problem. So yesterday problem we are solving, dy it is coming, the velocity vector dot area vector. Area vector where it is? The area magnitude is dy into width. Area magnitude. This area we are talking about, this area. So this area dy dot width, and if you vector is the positive x-axis. So I, it's a positive x-axis. So dy w positive x-axis, because from the area outward normal. If you draw the outward normal, it will be in this side area. On the same way here, along dx, so Vj is the velocity, and from here, if you draw the outward normal from this dx, if you draw the outward normal, so what is the here? Dx into w. Dx into w. And the velocity is also will become here, that is the j. In this way, we are getting the problem the previous day. And we got a solution of here, that is, the solution comes as a streamline difference. But today we'll see the problem in a different manner. It's how it is. If you take one small elemental area, dl is the small elemental area. This is the dx view. It's a theta angle. So velocity vector across this thing is ui plus vg is the velocity. ui plus vj is the velocity vector across this. Now, the area vector is the area vector, unit vector eta. Area unit vector is eta. So eta is, that is the eta. This side is a j vector. This side is a negative I vector. Negative I vector. And as this angle is theta, so here also this angle will be theta. Here also this angle will be theta. So the vector n vector, we can write minus I cap cos theta plus j cap sin theta. So V dot NdA. What is the dA here? dA is nothing but dl into. So that is the flow rate across the point. So if you do this performance, it will come as a minus u dl cos theta into W plus v dl sin theta. So in this triangle, if you take the cos theta is equal to dy by dl, and sin theta is equal to dx by. If you put here, so dl cos theta is nothing but dy plus dl sin theta is nothing but dx. So this is nothing but here, that is the d of psi, change of streamline change into here. So total flow across 2 points, the total flow across 2 points will be equal to the 0.2 minus 0.1 into width, or it may be the reverse. So it is always coming in this way. So that is another way to solve this kind of a problem. This is another way to solve this kind of a problem. So over the line element, what is the flow rate? Flow rate is the volume dot product of the area vector. Velocity dot area will gives you the volumetric flow. That is the way to solve this kind of a problem. Next question, again repetitive one question, the streamline question they are asking. We simply will see what is the answer. Here, x is given 2xy, u is equal to 2xy, and v is equal to minus y square, streamline equation. This is a very, very important question they're asking always. Simply you put it here in this equation, do the integration, you will get the answer. So one y will be cut out here. So dx by x is equal to minus 2 dy by y. So if you do this, perform this integration, it becomes ln x minus 2 ln y plus ln c, any constant. So ln x y square is equal to ln c. So x y square is equal to c is the answer. So this is a simple question we have done. It is here, the previous question, it should be mod. Why? It may be the difference between the 2 and a, any 2 points. And in a streamline, if you take one fixed point and another the variable point, this variable point B may be any location of the same streamline, but the flow across would be the same, no changes. If B may be, there is a streamline across streamline over the B. So this B point may be at here, but the flow rate will never changes. Next question is coming. You are asked to evaluate the assorted fluid flow for their suitability in their given laboratory application. Here, the choice is given to you, and they are asking you, so which flow is better to be, say, incompressible and irrotational flow? So incompressible flow means, so divergent of velocity vector is equal to 0. And irrotational flow is the curl of velocity vector is equal to 0. So out of this PQR, which is satisfying both? Which flow is better to choose? So as it is the two-dimensional cases, so this can be reduced to du dx dv dy is equal to 0. And this can be reduced to dv dx minus du dy. Two-dimensional case. If you perform, so because it is a k dot, k only exists, it's like this way as a vectorically. So that means this term should be 0. So if you perform this thing which is satisfying, this will give the answer. So here, u, if you go for the u, so the number p is satisfying incompressible but not satisfying. It's not satisfying irrotational case. Here also said, you try with the r, u is given as a minus 2x and v is given as a 2. So if you go for du dx dv dy performed, it becomes minus 2 plus 2 to say. On the same way, if you go for dv dx minus du dy, so dv dx there is no x term, so 0, minus the y there is no, so that is 0. So r is a suitable choice here. R is a suitable choice. So there is a 3 option, A, C, and D. Next, P is not suitable for irrotational flow. If you put it here, you see for the P is, so del u del x for the P, in case of the P, del u del x plus del v del y. What is the value is coming? So del u del x is 0, del v del y is 0, this is 0. But dv dx minus du dy. So dv dx is coming minus 3 and du dy is coming minus 5. It's not equal to 0. So it is a rotational flow. It is a rotational flow. P is a rotational flow, but incompressible. So this option also cut. So A cut. So C and D. So Q you have to verify. In the case of the Q, du dx plus dv dy. If you do this, so it is coming 3y plus 0. So it is not an incompressible flow. It is not an incompressible flow. And not a, so it is not valid. Not a rotation also. If you try for the rotation, if you do this operation, dv dx minus du dy, it becomes minus dx. So it is not a rotation, it is a compressible and rotational flow. So your answer will be only P. Now here in the incompressible flow, incompressible fluid is here, in their subfluid is. In here some fluid is. Now you're asked what is happening. This moving circular plate is moving with the velocity. The same type of the problem is appeared here. This is the velocity with v. It is coming down. The circular plate. It's a circular plate. So at location R, if you take one small elemental area, control volume. In the location R, if you take one small dr, you're taking, and you see here, as it is the moving plate is coming down, as the moving plate is coming down, so what is the effect is coming over there? So what is the radial velocity at radius R? When the gap is h. The gap is h at that condition. This problem we'll see. So here at R, you are asked to, because as this is coming, this plate is coming downwards with the velocity v. So whatever the fluid inside, trapped fluid, it is going in this direction. Fluid is going in this direction with the velocity of Vr. With the velocity of Vr. You are asked to finding out what is the Vr, first question. So same way, same concept, as it is coming down. So what is the volume is decreasing, the same liquid is passed through it. So V. So as it is coming down, V into the circular area of the circular plate. So area of the circular plate is pi r square. But here we are taking only at radius r. So only radius at r. So we are better to write it. This area we are considering only this area, this circular area up to r, smaller, not capital. So here not capital R, here would be radius small r. That is the flow. That much flow is because V is coming down, so V into area is here. That is displaced by this over this area. So that is nothing but VR into this area. What is the area? The area is the 2 pi r into h. 2 pi r in, as it is a circular, so total periphery into the height. So over this area, the radial velocity is going up. So hence, VR is equal to VR by 2h. That is the answer. So as the moving circular plate is going down, getting down, so it's nothing but a continuity equation. In integral form we are writing. So how much the flow is, because it is pressed over the liquid and liquid is going out in this. One more thing, this V, the circular moving plate is moving, the V, that is nothing but we can write it dH by dt. That is nothing but dH by dt. Because H is a function of T. Because with the time, the H is changing. The gap is always changing with the time. The gap is always changing with the time. So what is they are asking, what is the acceleration of it? What is the acceleration of it? So if you go for it, so acceleration of it means del Vr dt. You have to perform this operation, del Vr dt. So del Vr dt is so V is not a function of T, R is not a function of T, only H is as a function of T, H. So H square into dH dt. One minus negative sign will appear here, but you are taking only magnitude. You are taking only here magnitude. So this dH dt, because gap is changing. Why? Because of the velocity capital V. The gap is changing. The rate of change of the gap is nothing but the velocity. So we can write it down. V at R is equal to capital R they are telling. So R you can replace by capital R. At R is equal to capital R. So VR by 2h square into v again, because this is nothing but the v. So rate of change of gap is nothing but the velocity of the moving circular plate downward direction. So this will give you v square r by 2h. So your answer is a C in this case. So this kind of the problem, if you given, you just telling this thing, whatever the volume changes here, the same volume is going out. Same volume is going out from this. So circular plate is pressing the amount of the liquid. It occupies the volume that much, the volume is escaping. That is the case.